So, this is the, like, part of 5.6 related rates. We'll do some out of the book too, but I think it's easier to start with this worksheet. The teacher that I worked with, when I did student teaching, he would always start out with, like, this worksheet when he taught them, or, like, a worksheet like this, and then he would go and do some other examples outside of this, but I think this is a fair little assessment. So, anyways, but related rates, basically these are just word problems, as you can see. Example 1's listed there. It's a pretty intense word problem. So it says to identify all given quantities and quantities to be determined, make a sketch and label the quantities. So some things I will make a sketch, some things not as much. It just kind of depends, but they can be helpful in some things especially. And then write an equation involving the variables whose rates of change either are given or are to be determined. Using the chain rule, implicitly differentiate both sides of the equation with respect to t, so everything's with respect to time. And then after completing step 3, substitute in the resulting equation all known values for the variables and their rates of change, and then solve for the required rate of change. So the rates of change are basically like our derivative values, how we were doing in the last section. We would do like dy equals blah, 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 dx. Well, dx is going to be like our rate of change values that we're using for these different problems. So, example 1, a police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with the radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So, I've got the cruiser. I've got a car over here. And this is the intersection. So, cruiser's coming down this way. Then makes the turn. And we've got this value here also for the distance between. Now, technically, this last one isn't really an arrow. It's not really going that way. The other arrows are dictating the direction that he's going, but it's fine. All right, so we've got a right-angled intersection. This is Y. This is X. This is Z. Typically end up using Z for these kinds of things, but it just depends. All right, so gonna write down stuff that I know and figure out what I'm trying to solve for. So X is 0.8 miles to the east, so 0.8. And then Y is from the north, 0.6 miles. And then Z, they said they determine, oh, we don't know that yet. We'll figure that out in just a second.
I have a feeling it's going to be 1 mile.
Yeah, it is.
Because Pythagorean triple.
Yeah, true.
Three, 4, 5, scaled up, or well, down.
Scaled down.
Yeah.
Yes.
Scaled up and then scaled down.
So, anyways, yes, so we can just go ahead and fill in that's 1. We don't really need to show that. I trust that you either know that it's a Pythagorean triple or that it's easy math to do a Pythagorean theorem to figure it out. So 1 mile. Now these other values, dx dt, dy dt, Never leave myself enough space. dz dt are the rates of change.
This just sounds so funny.
So let's look at what they told us. They told us that the distance between them, so the dz dt, is changing at 20 miles per hour. So this is 20. I'm just going to write mph. Then they said if the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So dx dt is what we're trying to find. So I usually put a question mark there to begin with, and then once I find it, I'll erase the question mark and then replace it with what it is and then circle that answer. dy dt is 60 miles per hour. Now, he's moving south, right? He's coming from the north, he's going south. So that's going to be a negative value. So negative 60 miles per hour. All right, so we know the Pythagorean theorem. So kind of like we were doing with optimization, when we had to like pick a formula that we knew, we're doing a similar thing here. And we're going to be taking the derivative implicitly of everything. So we've got x squared plus y squared equals z squared. So then we take the derivative of everything implicitly because everything is with respect to t. So this is going to be 2x dx dt plus 2y dy dt plus 2z dz dt.
I was gonna write 2x x prime. Would that have been the same thing, technically?
Well, we need to specify because there's not a t in here. So when we did implicit differentiation before, we would do like dy dx, or we would write it as y prime, but it was clear that we were doing it with respect to x, but since there's no t here, we need to do them as the actual rate.
Why does that say plus 2z dz?
I don't know. I'm not paying attention. So I know which piece I'm trying to solve for, so I want to move everything else over. So I'm going to move over the 2y dy dt by subtracting, and then I'm going to divide by 2x. So I've got dx dt equals 2z dz dt minus 2y dy dt divided by 2x. So obviously, under normal circumstances, we'd factor out the 2 on top, then we'd cancel it with the bottom. But since I can clearly see there's a 2 in everything, I'm going to cancel out all these 2's. Then plug in dx dt equals, I'm just plugging in numbers, 1 times 20 minus 0.6 times negative 60 divided by 0.8. So then a lot of times what I'll do is I'll come over here and I'll erase this and I'll write in.
I don't know, I was kind of expecting it to be moving faster. Although, I'm not sure if it's scary, entertaining, or both to imagine that car taking the turn at the intersection.
Yeah. I would imagine they would have had to slow down a little bit, but so would the cruiser. So it's kind of more like average, I guess you could say. I mean,
I'm just imagining them drifting around the turn.
yeet. You never know. All right. A pebble is dropped into a calm pond. I'm sure you've seen this before. You're just like bloop, and it's like. Anyways,
now the pond is all
ripply.
discombobulated.
Yeah, it causes ripples in the shape of concentric circles. That just means that they keep expanding outward. Anyways, the radius of the outer ripple is increasing at a constant rate of 2 feet per second. When the radius is 4 feet, find the rate at which the area of the disturbed water is changing. That had to be a large pebble.
What if the
Because a little itty bitty pebble, like that I think of pebble, it wouldn't be changing at 2 feet per second. That's not a pebble, that's a rock. Like, I don't know. Maybe I'm just overthinking it, but it seems a little crazy. But it is
does
math
seem
class,
insane.
and in math class, people buy 75 watermelons, and nobody questions why.
and
Anyways.
then for some reason they eat like 64 of them in an
Yeah.
hour.
Exactly. All right, so there's my pebble.
I was wondering what that was.
Dropped into the water.
Pebble.
Do, 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 do. Oh, wait. I guess I should do it like this. And then it's like, wee, wee. I guess I should actually make these good circles since I can. Nope, that's an oval. Come on, buddy. Help me out here.
Apologies, I cannot assist you.
Good enough. Be like, why'd you draw a target on the paper? Dartboard. All right, so find the rate at which the area of the disturbed water is changing. So I know that the formula that goes with area of a circle is what?
IR squared.
Yep. So I'm going to leave that there. Sometimes, I didn't do this in the last problem. I drew the picture first, and then I went through and I labeled everything. Then I chose my formula. Sometimes I actually like doing the formula first, just because it can help me with determining what pieces of information I don't have and I do have and whatever. So there's that. So area, so A equals, and we've got R equals, and then I've got dA dt, and I've got dr dt. Now, there are also pieces of information that sometimes are unnecessary. Okay, like that I'm not going to need that number. So up here, I needed all of these numbers to get plugged in. I needed X, I needed Y, I needed Z, and I needed all of the rates of change, right? Well, when I take the derivative of this equation, what's going to happen with respect to T?
A is just gonna go to like dA dt.
Yeah. So I'm not even going to need A, is where I was going with this. Now, can I find A?
Might as well.
I can, and I usually do just because, but just to know, like, there are going to be pieces of information either you may not really be able to easily figure out, they may just flat out not give you, whatever, and that's fine because you probably don't need them if that's the case. So yes, I could find area by doing pi times 4 squared, and I could just call that 16 pi if I was so inclined. But it's not information I'm going to need, so I'm just going to put a line through it, just saying, hey, it's unnecessary.
Yeah.
And I guess if I want to be completely accurate, I should say feet squared.
I was about to mention that.
Now, the radius is 4 feet, so I've got that here. The radius of the outer ripple is increasing at a constant rate of 2 feet per second. So that's R, dr, dt. So that's 2 feet per second. Then dA dt is what I'm trying to find, which is nice. This one's already going to be solved out. What's the derivative of this side?
2 pi r dr dt.
Yep, 2 pi r dr dt. Now I just plug everything in. dA dt equals 2 pi times 4 times 2, which is 16 pi feet squared per second. Now, some people will go ahead and multiply the pi through. Some people just leave it. I don't really care. Typically on this one, I just leave it for the sake of the example, but it really doesn't matter. If you gave the decimal number, it'd be fine.
On the AP exam.
They should take it. It should be one of those they would take it either way if you had it as a short answer question. If it was a multiple choice, obviously, you'll be able to tell.
Yeah.
They're not going to give you both and expect you to know which one to pick.
Right.
Now, I will also say, I kind of mentioned this the other day, I think, but they used to always have a problem like these on the AP exam. They have kind of gone away from that, it seems. That if they do, it's like one, and it typically is going to actually be a problem like the next one, which I got to go to my other paper for.
Virginia's really missing out.
What do you mean?
She doesn't get to draw stuff live with us. She has to wait until you post the video.
True. Let me see.
Well, I guess it would be a
Is
good
this
idea to
one?
remind her that we have a quiz in calculus next Monday.
Yeah. Well, that also is all dependent on when we finish this stuff up, but
Yeah, I guess.
it should stay Monday. It shouldn't be a problem, but you never know. All right, so.
Like what we always do in math.
True. All right, so this next one, typically this problem, where it's like a conical tank and water
It's not like
rising or falling out of it or whatever, depending on the situation, or like sand coming out of a tank. This kind of problem, if you got one on the AP exam, is what it's going to be. Like your related rate is going to be one more like this. It always has been.
So is
At least from what I've been told. Now, if that's false information, that I was given false information.
so conical, is that cone
No, like a snow cone.
or a traffic cone?
Sure. My AP practice books haven't really been giving many of these short answer questions. I think I was able to find like one last year, and I was like, man, like this is always on there and whatever, but I think they've kind of changed the AP exam slightly, because the year I was working with that teacher was like fall of 2016, I think. So, and he said that there was always one like this on there, but now I think they've kind of gone away from it. So it's still good to make sure we know how to do them, because it is something that's covered in there, obviously, but they're not necessarily, like I think last year it was a multiple choice question that they had. It was not a short answer question on the AP exam last year. So, which is just interesting to me, but YOLO. So, I've got a conical tank.
That's comical. Not gonna lie, I would have drawn it the other way for some reason. That would have been really silly though. 'Cause,
Stands point down.
well, like I said, that would have been really silly. I did not register register that part of it, but
Minor details. All right, so we've got water running into a conical tank at the rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Okay, so
I want to know how many conical feet per minute the water is running. I just want to know that.
all right, so the height of this cone is 10 feet.
There we go. I can see it now.
The base radius, so even though it's point down, the base is still this part up here.
Naturally.
So this base radius here is 5 feet. It means the cone at the top is as wide as it is tall. Which is interesting. And then we know that it's got water in it. Now, before I write out all my known stuff, what is the formula for volume of a cone?
This might take a moment.
Okay. I can wait. I think we should have nap time.
Yes, please, yes. Okay. So are you prepared for a wrong answer?
Yes.
Okay. 1/3 pi r squared h. Okay, so she's writing it down.
Because you're right. So, and that makes sense because if you took a cone is like a triangle, right? If you just looked at it at face value without it being rounded. And so then it's like another triangle on each side. So 1/3 makes sense. Now, the pi r squared is the area of a circle, right? And then times h for the height to give us
So
going all the way down.
So pi r. What would be the surface area of the
I
Like pi-
would have to look that up. That's not one I know off the top of my head.
Because like I know the surface area of a sphere is 4 pi r squared, and then like the volume of it, it's 4/3 pi r cubed. So I'm wondering if that the 1/3 thing is kind of.
I'm sure it is. That's not one I know off the top of my head. However, volume of a cone, you need to make sure you know for the AP exam.
Okay. Well, apparently I know that.
Clearly you do. But more for Virginia. Make sure you know this formula.
Right. Yeah, Virginia definitely would have remembered.
Tell us in our group chat if you understood that question or statement, whatever. All right, so whatever. Don't laugh at me, Josh.
I'm not laughing at you.
Sure, you're not.
I'm just laughing in general.
All right, so I'm going to move this back over here. It's going to cover up the 10 for a minute, but I need the space.
Well, at least I know it exists.
All right, volume. Again, we can find this, but do we need it?
I guess not.
No, we don't. So I'm going to just not fill it in. dV dt is the rate at which the volume is changing. So that's 9 cubic feet per minute. So 9 feet cubed per minute. Now, we know the height of the water. It's at 6 feet. And then DHDT, how fast is the water level rising, is what we're trying to find. Now, under normal circumstances, what else do you think I also need?
Radius, I guess.
Yes, but I'm going to see if there's a way that I can find it, because I actually need the radius here where the water level is, right?
Oof.
But I don't know that.
I don't know
Correct.
that either.
So a really common mistake is people write down the radius is 5. It's like it's 5 at the base, but that's not what I'm actually dealing with. I want it when the water is 6 feet deep. Like, that's specifically what I care about. So I'm going to be looking at this area in here. Okay. So I'm going to redraw this as a triangle. With my water level here. Top of water. Alright, now this up here is the top of the tank. Obviously this is not drawn to the scale that I drew the other thing to, but it's mainly because didn't leave enough space to do that.
I understand.
I know that this whole piece is 10 feet. So the radius that I'm looking for is here, and this is H here. And obviously the top of the tank, this radius is 5. So I'm going to use similar triangles to go about finding what I'm trying to solve for. So this little area here in the middle, I'm going to look at as R over 5 equals H over 10. So this is little triangle over big triangle. So that means that R is equal to 1/2 H. So I'm going to take and use this in my original formula here for R, so that I'm only dealing with one variable, which is going to be another thing that we often end up doing, unless they give us all the information, but a lot of times we're going to be rewriting things in other variables. So V equals 1/3 pi times 1/2 H squared times H. So when I square this, that's 1/4 H squared. So this is going to be V equals 1/12 pi H cubed. Now I take the derivative, dv dt. You gonna laugh this time?
No, I'll just smile.
Equals 1/4 pi H squared dh dt. I'm solving for dh dt, so that means everything else is going to get moved over. But I'm going to go ahead and plug in. So I've got 9. I'm going to go ahead and multiply by 4, divide by pi, divide by h is 6 squared, equals dh dt. And part of the reason I'm doing it like this is because I'm running out of space. But I think you can follow what I'm doing. Maybe.
So,
I plugged in 9 here.
right, I'm just rewriting it so that I know what in the world is going on.
Virginia, I hope I didn't just confuse you. I'm just running out of space.
Okay, so the 9 is the D.
It's the dv dt. Multiplied it by the 4 from the 1/4.
And we have the pi.
And I divided by pi. I plugged in 6 for h, so I divided the whole thing by 6 squared, aka 36. So on top I've got 36, on bottom I've got 36, so I end up with 1 over pi feet per minute. One over pi feet per minute is the rate that it's changing at.
The drawing the picture part is very helpful.
Yeah, and some of them it is helpful to have it. Some of them, like, it doesn't really make that much of a difference, like, just gonna be honest. But, like, especially for these ones, like, with a cone where you're, like, need a similar triangle, like, it's much more. There's one in your packet that's something about, I think, or at least I think it's in there, about sand falling out of a tank. But that one is one that will be similar to that, but it falls out in a conical pattern. So instead of it being point down, it's point up. Just kind of interesting. All right.
Oh, I think I just understood the volume formula of the cone and the surface area. So wouldn't like the surface area of a cylinder be pi r h? Would there be a 2 in it?
I'm not sure. I would have to look it up. I would say probably not, since there's not in the area of a circle. But it's hard to know for sure.
Yeah, I was just thinking about that, and like I thought I was imagining taking a cone out of a cylinder and like how much of the cylinder is left.
2/3 of it. Yeah.
So that would explain 1/3.
Right.
I'm sure I'm confusing Virginia even more.
Yeah, Virginia, just disregard the last 30 seconds. I'm just kidding. All right. We might only do part A because I want to give you some time to look over your government. But
Thank you.
I don't know how much time you need, but we'll just do.
Eternity and a half.
A ladder 25 feet long is leaning against the wall of the house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. I actually watched, have you ever watched Fail Army on YouTube before?
Yes.
Okay,
We're subscribed to them even.
I'm not even gonna lie. We watched one guy the other day where his ladder literally fell away from the house. Like, it started sliding down the wall of the house, like this problem. And I was literally like, I'm about to teach this week. That's crazy.
It's like a revelation or something.
Fun fact. All right, how fast is the top of the ladder moving down the wall when the base is at 7 feet, I guess is technically what it's supposed to say. So, picture here. So, this is the ladder. I think L makes sense for that. This is the wall, which is Y. This is the ground, which is X. And you don't have to use L for ladder, obviously. I just think it makes sense, so I did.
I wrote L adder.
L adder. All right, so then I've got X, Y. I was about to write Z, L, and then dx dt, dy dt, dl dt. All right, so it's supposed to say, I think, when the base is 7 feet from the wall. So X is 7 feet. Y is, oh, I don't know yet. The ladder is 25 feet long, so that's the hypotenuse, so that's 25 feet. know what this one is?
18 just sounds right for some reason, but I know it's not. I do not know that one.
My calculator's not over here, but I'm pretty sure it's
21, maybe?
nope. 625 minus 49, 576, square root of 576.
24.
Yeah. So 24 feet, again, just from the Pythagorean theorem, we can figure that out. Now, dx dt, I know that it is, the base is being pulled away from the wall at 2 feet per second. So that means dx dt is 2 feet per second. Now, can the height of the ladder change? And don't get smart with me.
Why would I get smart with?
I
Oh.
said that one time and someone went, well, my dad has an adjustable ladder. So that's why I said,
Ladder
don't
goes
get smart with me.
Ladder does that.
Yes.
But now we're just assuming it's one of those stiff ones.
It's a set ladder that cannot change in length. So I don't need to worry about that. DLDT isn't even possible. The ladder does not change.
Okay, so I'm saying that one equals meh.
Sure. Yeah.
Makes sense to me.
Height doesn't change. All right, so now I'm solving for dy dt. So I've got x squared plus y squared. I think it's because it's at the crack on my iPad that it just did that. Equals L squared. Now,
I mean, it did say oh.
because we know that the ladder length stays constant, I will go ahead and replace L with 25. So x squared plus y squared equals 625. I just plugged in the number. Now I take the derivative. What's the derivative of this?
2x dx dt plus 2y dy dt equals 0.
Yep. Now I want to solve for dy dt. So I'm going to subtract this over, divide by 2y. So dy dt equals negative 2x dx dt divided by 2y. Obviously, y's, or not y's, 2's cancel. So I have negative 7 times 2 over 24, which will reduce down to, what, 7 over 12, negative. So it is sliding down the house. That's what the negative means. At negative 7 over 12 feet per second. Basically, the negative just implies it's going down, which makes sense. Can't slide up. I guess it could if you were intentionally pushing it up, but anyways, we'll do the part B of this one tomorrow. I always had to make sure that today's not Friday. Part B of this one tomorrow, and then
Right, it's Tuesday.
y'all will have some a few to do. Oh, we'll do one more after that, and then I'll probably give y'all a few to do, and then we'll go through and maybe do some out of the book also. I have a few that I normally pull and do, but I like this worksheet better.